And now in this lecture we'll answer two questions. In the first question, we'll find out the size of this angle ABC is equals to x. So we have to find out the value of this angle, angle x. In the second question, we'll find out the length of this side AD is equals to x. So we have to find out the value of line segment x is equals to AD. So we start with the first question. In the drawing, we have quadrilateral ABCD. Those triangles are both equal to 80 degrees in their sizes. In addition, we know that BC equals to BA equals to AD. Again, our test is to find out the size of this angle ABC is equals to x. So we have to find out the value of this angle, angle x. So first of all, we will join points B and D together by a straight line. By joining points B and D, we divided quadrilateral ABCD into two triangles. We have the upper triangle BCD and the lower triangle PAD. We have the rule that says that in front of equal sides in the triangle there are equal angles. Again, in front of equal sides in the triangle there are equal angles. So in triangle ABD, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to the rule that I mentioned. We know that the sum of the angles in a triangle is equal to 180 degrees. Therefore, the sum of the angles in this triangle ABD must be equal to 180 degrees. So which angles we have in the triangle ABD? We have alpha plus alpha is 2 alpha plus 80 degrees. In total must be equal to 180 degrees. So 2 alpha plus 80 degrees. In total the sum of those two angles must be equal to 180 degrees. And again, in triangle ABD, the sum of the angles must be equal to 180 degrees. That is to say, 2 alpha plus 80 degrees, it must be equal to 180 degrees. Here we will subtract 80 degrees from this equation, and we get that 2 alpha equals to 180 degrees minus 80 degrees equals to 100 degrees. So 2 alpha equals to 100 degrees. Here we divide this equation by 2, and finally we get that the missing angle alpha equals to 100 degrees over 2 is 50 degrees. So here, this is the missing angle. Those two angles are both equal to alpha, therefore each angle equals to 50 degrees in its size. What is the size of this angle? Angle CDB. The size of this angle CDB equals to 80 degrees minus 50 degrees, that is 30 degrees. In the next step, we define this angle, angle BCD, as beta And we will implement the law of sines in this triangle BAD. So I put quickly on the law of sines. The law of sines is true in any triangle. So actually, this is triangle ABC that could be any triangle. The length of side AB equals to C units in itself, side AC equals to B units in itself, side BC equals to A units in itself. This angle BAC is equals to capital A degrees in its side. Likewise, this is angle ACB is equals to capital C degrees in its side. And finally, this is angle ABC is equals to capital B degrees in its side. So in this triangle ABC that could be any triangle according to the law of sines. The following equation is to A over sinus A equals to B over sinus B equals to C over sinus C. Again, in this triangle ABC according to the law of sines, the following equation is to A over sinus A equals to B over sinus B equals to C over sinus C. So you can actually implement the law of sines in our triangle ABD. So in this triangle ABD, according to the law of sines, the following equation is true. BD over sinus 80 degrees equals to BA over sinus 50 degrees. And again, in this triangle BAD, according to the law of sines, the following equation is true. BD over sinus 80 degrees equals to BA over sinus 50 degrees. In the next step, we'll define the length of side BA as A. And because of the fact that BA equals to AD equals to BD, those three sides are equal to each other, so those two sides must be also equal to each other, and must be also equal to A units in their length, because all those three sides are equal to each other. So BC equals to A, and AD also equals to A. So according to the law of sines, BA over sinus 50 degrees. So BA is A, so let's substitute BA by A. Or sinus 80 degrees. We'll substitute 80 degrees by 2 times 40 degrees. So sinus 80 degrees equals to sinus 2 times 40 degrees. So in this equation we have A over sinus 2 times 40 degrees equals to BA. Again, actually we have here BD. BD is the missing side, so believe this it is. So it is BD over sinus 2 times 40 degrees equals to BA. BA equals to A, so we substitute BA in this equation by A. A over sinus 50 degrees. We substitute 50 degrees by 90 degrees minus 40 degrees. So sinus 50 degrees equals to sinus 90 degrees minus 40 degrees. So those we found out that according to the law of sines, in this triangle ABD, the following equation is true. BD over sinus 2 times 40 degrees equals to A over sinus 90 degrees minus 40 degrees. In the next step, I present to you two trigonometric identities, and we'll implement the trigonometric identities in our equation, this equation. The first trigonometric identity is as follows. Sinus 2 alpha equals to 2 times sinus alpha cosine alpha. This is the first trigonometric identity. Sinus 2 alpha equals to 2 times sinus alpha cosine alpha. And the second trigonometric identity is as follows. Sinus 90 degrees minus alpha equals to cosine alpha. So we have here BD or sinus 2 times 40 degrees. Sinus 2 times 40 degrees, according to this trigonometric identity, sinus alpha equals to 2 times alpha, 2 times sinus alpha cosine alpha. So sinus 2 times 40 degrees, according to the first trigonometric identity, must be equal to 2 times sinus 40 degrees times cosine 40 degrees. And it is equals to A for sinus 90 degrees minus 40 degrees. According to this trigonometric identity, the second trigonometric identity that says that sinus 90 degrees minus alpha equals to cosine alpha, we will get that sinus 90 degrees minus 40 degrees equals to cosine 40 degrees. So in total, we shall find out that BD over 2 times sinus 40 degrees cosine 40 degrees equals to A over cosine 40 degrees. Here we have cosine 40 degrees on both sides of this equation, so cosine 40 degrees will get cancelled. After we cancel cosine 40 degrees, in this side of the equation we left only with A equals to BD over 2 times sinus 40 degrees. So in total, we shall find out that BD over 2 times sinus 40 degrees equals to A. Here we will multiply this equation by 2 times sinus 40 degrees. And we get that the missing side BD equals to 2A times sinus 40 degrees. And again, we shall find out that the missing side BD equals to 2A times sinus 40 degrees in its length. This is the missing side BD. This equals to 2 times A times 40, 2 times A times sinus 40 degrees in its length. So I write it down. BD equals to 2A times sinus 40 degrees in its length. In the next step, we will implement the law of sines in this upper triangle, triangle BCD. And again, we will implement the law of sines in this great upper triangle, triangle BCD. According to the law of sines, in this upper green triangle BCD, BC over sinus 30 degrees equals to BD over sinus beta. Okay, again, this green upper triangle BCD according to the law of sines, the following equation is true. BD over sinus 30 degrees equals to, so it is BC over sinus 30 degrees. BC over sinus 30 degrees equals to BD over sinus beta. BC equals to A, so we'll substitute BC by A. Over sinus 30 degrees. Sinus 30 degrees equals to 1/2. So we'll substitute sinus 30 degrees by 1/2. So in total, in this side of the equation, we have A over 1/2 equals to BD. We just find out that BD equals to 2A times sinus 40 degrees over sinus beta. So in total, we should find out that A over 1/2 equals to 2A sinus 40 degrees over sinus beta. A over 1/2 is 2A equals to 2A times sinus 40 degrees over sinus beta. So here we have 2A on both sides of this equation, so 2A will get cancelled. Also we cancel 2A, in this side of the equation we left only with 1, 2A over 2A is 1, equals to sinus 40 degrees over sinus beta. Here we multiply this equation by sinus beta. And we get that sinus beta equals to sinus 40 degrees. If sinus beta equals to sinus 40 degrees, it means that beta equals to 40 degrees in its size. Beta equals to 40 degrees in its size. This is the first solution for beta. The second solution for beta is as follows. We have another trigonometric identity. The first trigonometric identity is as follows. Sinus alpha equals to sinus 180 degrees minus alpha. And again, the first trigonometric identity is sinus alpha equals to sinus 180 degrees minus alpha. So according to this first trigonometric identity, we will get that sinus 40 degrees sinus 40 degrees equals to sinus 180 degrees minus 40 degrees. So it is 180 degrees minus 40 degrees, it is 140 degrees. So this expression equals to sinus 140 degrees. Those two sides of the equation are equal to each other. That is to say, in total we found out that sinus 40 degrees equals to sinus 140 degrees. sinus 40 degrees equals to sinus 140 degrees. This is according to this third trigonometric identity. But we already found out that sinus beta equals to sinus 40 degrees. So probably what we already found out here, we already found out that sinus beta equals to sinus 40 degrees. But we just right now found out that sinus 40 degrees equals to sinus 140 degrees. So we can add here to this equation that sinus 40 degrees equals to sinus 140 degrees. Those two sides of the equation are equal to each other. That is to say, sinus beta equals to sinus 140 degrees. Sinus beta equals to sinus 140 degrees. And for this equation, sinus beta equals to sinus 140 degrees, we will derive that beta equals to 140 degrees in its size. So the second solution for beta is that beta equals to 140 degrees in its size. Well, according to the first solution for beta, beta equals to 40 degrees in its size. So we have two solutions for beta. Beta could be equal to either 40 degrees or to 140 degrees. So if we take a look again on our original domain, here we have this is the green upper triangle BCD. The green upper BCD, angle BCD equals to beta. So from the domain, it is very easy to see that angle BCD is definitely greater than 90 degrees. Again, this is angle BCD is equals to beta. Angle beta is definitely greater than 90 degrees. If beta is greater than 90 degrees, then beta could never be equal to 40 degrees, that is less than 90 degrees. So, in case of the first solution for beta, beta could never be equal to 40 degrees. So, we have the only other solution, the second solution for beta, that is actually beta equals to 140 degrees in its size. This is angle beta that equals to 140 degrees in its size. In this green upper triangle BCD, the sum of the angles must be equal to 180 degrees. So which angles we have here in this green triangle BCD, the upper green triangle BCD? We have 30 degrees plus 140 degrees. Plus this third missing angle, this actual angle DBC. In total, the sum of those three angles must be equal to 180 degrees according to the rule that I mentioned. Repeat again, in the green upper triangle BCD, 30 degrees plus 140 degrees plus the first missing angle DBC, in total must be equal to 180 degrees. 30 degrees plus 140 degrees is 170 degrees. So 170 degrees plus the size of the third missing angle DBC, in total the sum of those three angles must be equal to 180 degrees. Here we'll subtract 170 degrees from this equation, and we get that the missing angle DBC, the missing third angle DBC, is equal to 180 degrees minus 170 degrees is 10 degrees. So if you found out that the third missing angle DBC, this is the third missing angle DBC is equal to 10 degrees in its size. Our task is to find out the size of this angle ABC is equals to x. So we have to find out the size of this angle ABC is equals to x degrees. From the drawing, it is very easy to see that the size of this big angle ABC equals to 50 degrees plus 10 degrees, that is 60 degrees. So we found out that the size of the angle that we are looking for, it is actually the size of angle ABC that is equals to x degrees is equal to 60 degrees in its size. And again, the size of this angle ABC is equal to x degrees is equal to 60 degrees in its size. So we finish with the first question. In the next step, I will present to the second question of this lecture, and we will solve the second question by using two different methods. In this second question, our task is to find out the length of side AD is equals to x. So we have to find out the value of line segment x is equals to AD. So in the drawing, we have quadrilateral ABCD. We know that AB equals to BP. The short line segment DP equals to 1 unit in its length. This is line segment PC, it is equals to 4 units in its length. Those two angles are both right angles. And our task is to find out the length of side AD is equals to x. So we have to find out the value of this line segment x is equals to AD. So first of all, we will join points B and D together by straight line. By joining points B and D, we divided this quadrilateral ABCD into two parts. The first part is the right triangle DAB, the upper right triangle DAB, and the second part is the right lower triangle BCD. So we will implement the Pythagoras theorem on both those two right triangles in the first step. So first of all, we will implement the Pythagoras theorem on this upper right triangle ABD. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle ABD, here by PT is the relation for Pythagoras theorem. So in this upper right triangle ABD, according to the Pythagoras theorem, BD squared, that is the square of the hypotenuse, equals to AB squared plus AD squared. Okay, again, in this upper right triangle ABD, according to the Pythagoras theorem, the following equation is shown. BD squared, that is the square of the hypotenuse, equals to AB squared plus AD squared. BD is the missing hypotenuse, so we leave it as it is, so it is BD squared BD squared equals to AB squared. AB is also the missing side, so we leave it as it is. So it is AB squared plus AD squared. AD equals to x, and therefore AD squared equals to x squared. X is the line segment that we are looking for in this question. So in total, according to equation 1, we found out that BD squared equals to AB squared plus x squared. Likewise, we will implement the product theorem on this lower right triangle times BBC. Here by PT is the abbreviation for Pythagoras theorem. This lower right triangle DBC, according to the Pythagoras theorem, BD squared, that is the square of the hypotenuse, equals to BC squared plus CD squared. Repeat again, in this right lower triangle DBC, according to the Pythagoras theorem, the following equation is true. BD squared, that is the square of the hypotenuse, equals to BC squared plus CD squared. BD is the missing hypotenuse, so we leave it as it is. So it is BD squared equals to BC squared. BC is also the missing side, so we leave it as it is. So it is BC squared plus CD squared, or DC squared. DC in total it is 1 plus 4, that is 5. DC is 5, therefore DC squared is 5 squared, that is 25. So in total, according to equation 2, we should find out that BD squared equals to BC squared plus 25. This is according to equation 2. Well, according to equation 1, we already found out that BD squared equals to AB squared plus X squared. So we have two different equations for BD squared. Equation 1 and equation 2. Therefore, we will create equation 3 that says that BD squared according to equation 1 must be equal to BD squared according to equation 2. This will be equation 3. So according to equation 3, equation 3 says that BD squared according to equation 1 must be equal to BD squared according to equation 2. BD squared according to equation 1 equals to AB squared plus X squared. And it must be equal to BD squared according to equation 2. BD squared according to equation 2 equals to BC squared plus 25. So in total, according to equation 3, I should find out that AB squared plus X squared equals to BC squared plus 25. This is according to equation 3. In the next step, we will implement the Pythagoras theorem on this right triangle BPC. Repeat again, we will implement the Pythagoras theorem on this green right triangle BCP. According to the Pythagoras theorem, in this green right triangle BCP, BP squared, that is the square of the hypotenuse, equals to BC squared plus CP squared. Okay, again, in this green under BPC, according to the Pythagoras theorem, the following equation is true. BP squared, that is the square of the hypotenuse, equals to BC squared plus CP squared. According to what is given as equation, AB equals to BP. So we can substitute BP by AB, because they are equal to each other. So BP squared is AB squared. We substitute BP squared in this equation 4 by AB squared. Also the fact that according to what is given as the equation, BP equals to AB, even as in the question. So substitute BP squared by AB squared. So according to equation 4, BP squared is AB squared, and it is equal to BC squared plus CP squared. So according to equation 4, AB squared equals to BC squared. BC is the missing side, so we leave it as it is, so it is BC squared plus CP squared. CP is 4, therefore CP squared is 4 squared, that is 16. So in total, according to equation 4, we actually found out that AB squared equals to DC squared plus 16. This is according to equation 4, while according to equation 3, we already found out that AB squared plus X squared equals to BC squared plus 25. We copy the equation 3 from here to here. AB squared, according to equation 3, AB squared plus X squared equals to BC squared plus 25. But because of the fact that according to equation 4, AB squared equals to DC squared plus 16, we will substitute AB squared in this equation 3 by DC squared plus 16. So according to equation 3, we have here AB squared. AB squared according to equation 4 is BC squared plus 16. And we have here plus X squared, equation 3, equals to BC squared plus 25. So in total, according to equation 3, we should find out that BC squared plus 16 plus X squared equals to BC squared plus 25. Here we have BC squared on both sides of this equation 3, so BC squared will get cancelled. After we cancel BC squared in this side of equation 3, we left with 16 plus X squared. And on the other side of this equation 3, we left only with 25. So in total, according to equation 3, we should found out that 16 plus X squared equals to 25. Here we will subtract 16 from this equation 3. Then according to equation 3, X squared equals to 25 minus 16 is 9. So X squared equals to 9. Here we'll take out of this equation and finally get that according to equation 3, X equals to the square root of 9, that is 3. So we found out that the graph of this side AD is equal to X is equal to 3 units. So according to the first method, the graph of this line side AD is equal to X is equal to 3 units. So we finish with the first method. In the next step, I present to you how to find out the length of this line side AD is equal to X according to the second method. In the second method, we will do a construction. That is to say, we'll extend this side DC of this quadrilateral ABCD by 4 units. Repeat again, we'll extend side DC, this side DC of quadrilateral ABCD by 4 units. And we will define the edge of the extended line segment. This line segment, extended line segment, this point is point Q. So CQ equals to 4 units in itself according to our construction. Repeat again. The extended line segment CQ equals to 4 units according to our construction. This is one side of quadrilateral ABCD, therefore it is absolutely a straight line. When you extend a straight line by straight line, the result DQ is also a straight line. DQ is a straight line, so if you focus on the upper side of this straight line DQ at point C, here the sum of the areas must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of the straight line DQ at point C? We have this angle, this is the right angle, plus this BC angle, and so that the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this BC angle must be equal to 90 degrees in size. In the next step, we will join points B and Q together by straight line. By joining points B and Q, we can get the right triangle BCQ, this right triangle BCQ. So in the next step, we will prove that those two right triangles can go into each other according to side angle side rule. So we have to prove that this is the right triangle PBC. So this right triangle PBC can go to this right triangle BCQ according to side angle side rule. So, why those two right triangles can go into each other? First of all, PC equals to CQ equals to 4. Repeat again. Side PC of the right triangle PBC equals to side CQ of the right triangle BCQ. They are both equal to 4, and therefore they are equal to each other. CQ equals to 4 units according to our construction. And PC equals to 4 units according to what is given as a question. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. So actually this is angle PCB. This right triangle PBC, and it is equals to this angle PCQ. This right triangle BCQ. Okay, again we should find out that angle PCB in the right triangle PBC equals to angle BCQ in the right triangle BCQ. They are both equal to 90 degrees and therefore they are equal to each other. And finally, this is side BC, that is a common side that belongs to both triangles. So can I know that BC equals to itself is a common side that belongs to both triangles. So let it know. BC equals to itself is a common side that belongs to both triangles. So if you found out that those two right triangles can go into each other according to side angle side rule. So let it know. We should find out that the right triangle PBC congruent, this is the sign of congruent, to the right triangle BCQ according to side angle side rule. What is this side angle side rule? I should prove that those two sides and the angle that is included between those two sides in this right triangle PBC corresponding equal to those two sides and the angle that is included between those two sides. This right triangle, triangle BCQ. Therefore, those two right triangles can point to each other according to side, angle, side. Or repeat again, those two sides and the angle that is included between those two sides, this angle, in this right triangle PBC are constantly equal to those two sides and the angle that is included between those two sides, this angle, in this right triangle BCQ. Therefore, those two right triangles can point to each other according to side, angle, side rule. And from the fact that those two right triangles can point to each other, we will derive that their corresponding sides must be also equal to each other and their lengths. That is to say, the hypotenuse BP in the right triangle BPC is equal to the hypotenuse BQ in this right triangle, triangle BCQ. So BP equals to BQ. BP equals to BQ. And again, BP equals to BQ according to the rule that says that corresponding sides in congruent triangles are equal to each other. Those two right triangles can go into each other, and therefore their corresponding sides, that is to say BP and BQ, must be also equal to each other in their lengths. But we have already found, according to what is given as a question, AB equals to BP, or BP equals to AB. So we can write down that BP equals to AB according to what is given as a question. And for this equation, AB equals to BP equals to BQ, we will derive that those three line segments AB, BP, and BQ are all equal to each other in their lengths. In the next step, we will do a construction. That is to say, we will construct a circle around point B in such a way that point B will be the center of the circle and BA will be the radius of the circle. Repeat again, we will construct a circle around point B in such a way that point B will be the center of the circle and BA will be the radius of the circle that we will construct. So, we constructed this circle with the center B and radius BA. So, BA is the radius of this circle, so we define the radius BA as R. So, B equals to R. But we already found out that BA equals to BP equals to BQ. And BA is the radius, therefore BP must be also equal to radius that equals to R, and BQ must be also equal to the radius of this circle that equals to R according to our definition. The definition of a radius is a line segment that starts from the center of the circle and ends on the circle itself. So BA, the radius BA, starts at the center of the circle, that is point B, and ends at point A, that is the point of the circle itself. That is to say, the circle must pass through point A, because point A must be located on the circle itself. Likewise, the radius BP starts from point B, that is the center of the circle, and ends at point P, that is the point of the circle itself. Therefore, therefore, the circle must pass through point P, because point P is located on the circle itself. Likewise, BQ is also the radius of this circle. BQ starts from point B, that is the center of the circle, and point Q must be located on the circle itself. Or in other words, A, P, and Q, they are all located on the circle itself, or the circle passes from this circle passes from points A, P, and Q. Because of the fact that all those three line segments A, B, BP, and BQ, they're all the area of the circle. Therefore, the circle must pass from points A, P, and Q. This given us the question that this is the right angle. So DAB is a right angle, and therefore it means that DA is perpendicular to AB. Because of the fact that this is a right angle, DA is perpendicular to AB. Okay, again, according to what is given us the question, DA is perpendicular, this is the side of perpendicular to AB. But AB is the radius of the circle, that is equals to R. So from this equation, we will derive that DA is perpendicular to the radius AB. DA is perpendicular to the radius AB, and therefore DA is a tangent to this circle at point A. So found out that DA is a tangent to the circle at point A. DA is tangent to the circle at point A. Point A is the point of tendency of tangent DA with this circle. So from this coming some point D, we have tangent DA that is tangent to this circle at point A. Likewise, from the same common external point D, we have secant DQ that cuts the circle at those 2 points, P and Q. DP is the external part of secant DQ, and the length of the secant in total is DQ. So all the requirements of tangent secant theorem are satisfied, and therefore can implement here tangent secant theorem. So repeat quickly on tangent secant theorem. According to tangent secant theorem, if a tangent and the secant are drawn to a circle from the same external point P, this is the common external point P. From the common external point P, we have tangent P8 that is tangent to this circle, at point A. Likewise, from the same common external point P, this point, we have secant PC that cuts the circle at those 2 points B and C. Actually, PB is the external part of the secant, and PC is the length of the secant in total. So in this domain, the following equation is true. The square of the tangent's length equals to the product of the secant's all length and its external part. The length of this tangent is PA. So the square of this tangent is PA squared, and PA squared equals to the product of the external part, that is PB, times the length of the secant in total, that is PC. Or PA squared equals to PB times PC. Again, PA squared equals to PB times PC. So you can definitely implement the secant tangent secant theorem in our drawing, as I already mentioned before. This is the common external point D. From this common external point D, we have tangent DA that is tangent to this circle at point A. Likewise, from the same common external point D, we have secant DQ that cuts this circle at those 2 points P and Q. So all the requirements of tangent secant theorem are satisfied. Therefore, we can implement tangent secant theorem in our domain. If you focus on the common external point D, according to the tangent secant theorem, dA squared, that is the length of the tangent squared, equals to dP times dQ. dP times dQ is the product of the external part of this secant times the length of this secant in total, that is dP, that is dQ. So it is dP times dQ equals to dA squared. Again, dA squared equals to dP times dQ. So write it down. If you focus of the common sum point D. According to second tendency theorem, dA squared, that is the length of tangent dA squared, equals to the product of the external part of the second dq, that is dp, times the length of the second in total, that is dq. So in total, according to tangent secant theorem, I shall find out that dA squared equals to dp times dq. dA is x, therefore dA squared is x squared. And it is equals to dp is 1 times dq. dq in total equals to 1 plus 4 plus 4, that is 9. So in total, we shall find out that x squared equals to 1 times 9, that is 9. So x squared equals to 9. Here we take out of this equation and find again that x equals to the square root of 9, that is 3. So we shall find out that sine dA is equals to x equals to 3 units in its length. So we shall find out that on both methods that the length of this side dA is equals to x is equals to 3 units. So we finish with the second method of the second question. In the next step, I'll start the lecture. That is to say, we repeat on the solution of the first question, and then we repeat on the solution of this second question on both methods. In the first question, our task was to find out the size of this angle ABC is equals to x. So we have to find out the value of angle x. So in the drawing, we have quadrilateral ABCD. We know that AB equals to BC equals to AD. Those two angles are both equal to 80 degrees in their sizes, and our task is to find out the size of this angle ABC that is equals to x. So we have to find out the value of this angle, angle x. So first of all, we join points B and D together by side line. By joining points B and D, we divided this quadrilateral ABCD into two parts. The first part is the green triangle BCD, and the second part is this triangle BAD. We know that in front of equal angles in front of equal sides in the triangle, there are equal angles. In front of equal sides in the triangle, there are equal angles. So in triangle BAD, in front of those two equal sides, we have those two angles that must be also equal to each other and their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha, according to the only dimensions. We also know that the sum of the angles in any triangle is equal to 180 degrees. So in this triangle BAD, alpha plus alpha, that is 2 alpha, plus the third angle is 80 degrees, in total it must be equal to 180 degrees. And again, in triangle BAD, 2 alpha plus 80 degrees equals to 180 degrees. If subtracted 80 degrees from this equation, and finally found out that 2 alpha equals to 180 degrees minus 80 degrees, it is 100 degrees. So 2 alpha equals to 100 degrees. Here we divide this equation by 2 and finally found out that the missing angle alpha equals to 100 degrees over 2, that is 50 degrees. Those two angles are both equal to alpha, therefore each of them is equal to 50 degrees in size. What is the size of this missing angle? From the drawing it is very easy to see that the size of this missing angle in total equals to 80 degrees minus 50 degrees. 80 degrees minus 50 degrees is 30 degrees. So the size of angle BDC is 30 degrees. We define the size of this angle BCD is beta, and then we implemented the law of sines in this triangle ABD. So a quick quick on the law of sines. Actually, the law of sines is true in any triangle. This is triangle ABC that could be any triangle. This triangle ABC, side AB equals to C units in length, side AC equals to B units in length. This is side BC that equals to A units in length. This is angle BAC that equals to capital A degrees in size. This is angle ACB that equals to capital C degrees in size. And this is angle ABC that equals to capital B degrees in size according to our definition. So in this triangle ABC that could be any triangle according to the law of cosines, the following relation is to A over sinus A equals to B over sinus B equals to C over sinus C. Again, this triangle ABC that could be any triangle, the following equation, according to the law of sines, the following equation is to A over sinus A equals to B over sinus B equals to C over sinus C. So we can implement the law of sines. Now triangle ABD. So in this triangle ABD, according to the law of sines, BD over sinus 80 degrees equals to BA over sinus 50 degrees. Okay, again, this triangle ABD, according to the law of sines, the following equation is to BD over sinus 80 degrees equals to BA over sinus 50 degrees. We define BA as A, and because of the fact that BA equals to BC equals to AD, BC and AD must be also equal to A because they are equal to each other. All those three line segments are equal to each other. So BC equals to A and AD also equals to A. And according to the law of sines, we found out that BD over sinus 80 degrees equals to BA over sinus 50 degrees. BA is A, so substitute BA by A. So BD over sinus 80 degrees equals to BA over sinus 50 degrees. So BA is A, so here we have A over sinus 50 degrees. We substitute 80 degrees by 40 degrees times 2. So sinus 80 degrees equals to sinus 2 times 40 degrees. Likewise, we substitute 50 degrees by 90 degrees minus 40 degrees. Therefore, sinus 40 degrees equals sinus 50 degrees equals to sinus 90 degrees minus 40 degrees. So in total, we found out that BD over sinus 80 degrees is sinus 2 times 40 degrees equals to BA, that is A, over sinus 50 degrees. Sinus 50 degrees is sinus 90 degrees minus 40 degrees. So in total, we found out that BD over sinus 2 times 40 degrees equals to A over sinus 90 degrees minus 40 degrees. In the next step, I presented to you two trigonometric identities, and we implemented these two trigonometric identities in our equation, this equation. The first trigonometric identity is as follows. Sinus 2 alpha equals to 2 times sinus alpha cosine alpha. The second trigonometric identity is as follows. Sinus 90 degrees minus alpha equals to cosine alpha. According to this first trigonometric identity, we will get that sinus 2 times 40 degrees equals to 2 times sinus 40 degrees times cosine 40 degrees. Likewise, according to the second trigonometric identity, we will get that sinus 90 degrees minus 40 degrees equals to cosine 40 degrees. Yeah. So in total, we found out that BD or sinus 2 times 40 degrees equals to BD over 2 times sinus 40 degrees times cosine 40 degrees, and A over sinus 90 degrees minus 40 degrees equals to A over cosine 40 degrees. So in total, we found out that BD over 2 times sin 40 degrees cosine 40 degrees equals to A over cosine 40 degrees. Here we have cosine 40 degrees on both sides of this equation, so cosine 40 degrees will get cancelled. After we cancel cosine 40 degrees, in this side of the equation we left with BD over 2 times sin 40 degrees, while on the other side of this equation we left only with A. So in total, we found out that BD over 2 times sin 40 degrees equals to A. Here multiply this equation by 2 times sin 40 degrees, and finally found out that the missing side BD equals to 2 times A times sin 40 degrees. And if we found out that the missing side BD equals to 2 times A times sin 40 degrees. The missing side BD equals to 2 times A times sin 40 degrees. In the next step, implemented the law of sines in this upper green triangle BCD. According to the law of sines, in this green upper triangle BCD, BC over sinus 30 degrees equals to BD over sinus beta. But again, in this green upper triangle BCD, according to the law of sines, the following equation is true. BC over sinus 30 degrees equals to BD over sinus beta. Again, the entire BCD, BC over sinus 30 degrees equals to BD over sinus beta. According to our definition, BC equals to A, BC equals to A, and sinus 30 degrees is 1/2. So in total, in this side of the equation, we have A over 1/2. While on the other side of this equation, we have BD. BD is 2 times A times sinus 40 degrees over sinus beta. So in total, we found out that A over 1/2 equals to 2 times A sinus 40 degrees over sinus beta. A over 1/2 is 2A, so 2A equals to 2 times sinus 40 degrees over sinus beta. Here we have 2A on both sides of this equation, so 2A will get cancelled. So 2A over 2A is 1, and here we divided this expression by 2A, so after we divided by this expression by 2A, we left only with sinus 40 degrees over sinus beta. So in total, we found out that 1 equals to sinus 40 degrees over sinus beta. Here we multiplied this equation by sinus beta, and finally found out that sinus beta equals to sinus 40 degrees. If sinus beta equals to sinus 40 degrees, it means that beta equals to 40 degrees in its size. But here we have another solution for beta. According to the first trigonometric identity, sinus alpha equals to sinus 180 degrees minus alpha. And therefore, according to this trigonometric identity, we will get that sinus 40 degrees equals to sinus 180 degrees minus 40 degrees. 180 degrees minus 40 degrees is 140 degrees. So this expression equals to sinus 140 degrees. Those two sides of the equation are equal to each other. That is to say, sinus 40 degrees equals to sinus 140 degrees. If sinus 40 degrees equals to sinus 140 degrees, it means that so we found out that sinus 40 degrees equals to sinus 140 degrees. But we already found out that sinus beta equals to sinus 40 degrees. But sinus 40 degrees equals to sinus 140 degrees. So we can write that sinus 40 degrees equals to sinus 140 degrees according to this equation. And from this equation, sinus beta equals to sinus 40 degrees equals to sinus 140 degrees. We learned that those two sides of the equation are equal to each other. That is to say, sinus beta equals to sinus 140 degrees. If sinus beta equals to sinus 140 degrees, it means that beta equals to 140 degrees in its size. So the second solution for beta is beta equals to 140 degrees in its size. But according to the first solution for beta, beta equals to 40 degrees in its size. But if you focus on our drawing, you can see that this triangle BCD, the triangle BCD, this angle equals to beta. This angle beta, that is definitely greater than 90 degrees. If angle beta is greater than 90 degrees, angle beta can never be equal to 40 degrees, that is less than 90 degrees. So we cancel the first solution for beta. Beta can never be equal to 40 degrees, and we took into account only the second solution for beta, that is beta equals to 140 degrees in its size. This is angle beta, that equals to 140 degrees in its size. The sum of the angles in the triangle BCD equals to 180 degrees. So 30 degrees plus 140 degrees plus the size of this first BC angle, that is actually angle DBC. In total, the sum of those three angles must be equal to 180 degrees. Read again in triangle, the green triangle DCB, 30 degrees plus 140 degrees plus the third BC angle DBC. In total must be equal to 180 degrees. 30 degrees plus 140 degrees is 170 degrees plus the third BC angle DBC. In total must be equal to 180 degrees. Here we subtract 170 degrees from this equation. And finally found out that the missing angle DBC equals to 180 degrees plus 170 degrees is 10 degrees. So this is the missing angle DBC, that equals to 10 degrees in size. Our task is to find out the size of this angle ABC, that equals to x. So the size of this angle ABC is equals to x. In total it is equals to 50 degrees plus 10 degrees, that is 60 degrees. So we found out that the size of the missing ABC is equals to x degrees is equals to 60 degrees. So angle ABC that is equals to x is equals to 60 degrees in size. So we finish to repeat on the first question, the solution of the first question. In the next step, I'll repeat on the solution of the second question on both methods. Our task in the second question was to find out the length of this side AD is equals to x. So we have to find out the length of right side x is equals to AD. In the drawing, we have quadrilateral ABCD. We know that AB equals to BP, and we also know that those two angles are both right angles. This is right side BC, this is equals to 4 units in itself. This is the short right side DP, this is equals to 1 unit in its length. Again, our task is to find out the length of side AD, this is equals to x. So we have to find the length of line segment x is equals to AD. So we start with the first method. In the first method, we join points B and D together by straight line. By joining points B and D, we divided quadrilateral ABCD into two parts. The first part is this upper right triangle DB, and the second part is this lower right triangle DBC. So in the next step, we implemented the Pythagoras theorem on both those two right angles. According to the Pythagoras theorem, in a right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this upper right triangle ABD, according to the Pythagoras theorem, dB squared, that is the square of the hypotenuse, equals to AB squared plus AD squared. And again, this right triangle ABD, according to the Pythagoras theorem, BD squared, that is the square of the hypotenuse, equals to AB squared plus AD squared. BD is the missing hypotenuse, so we leave this it is, so it is BD squared equals to AB squared. AB is also the missing side, so we leave this it is, so it is AB squared plus AD squared. AD is x, therefore AD squared is x squared. X is the line segment that we are looking for in this question. So in total, according to equation 1, we found out that BD squared equals to AB squared plus x squared. Likewise, we implemented the Pythagoras theorem on this right lower triangle, DBC. According to the Pythagoras theorem, in this right lower triangle, again triangle DBC, BD squared, that is the square of the hypotenuse, equals to BC squared plus CD squared. Repeat again, the right lower triangle DBC, according to the Pythagoras theorem, BD squared, that is the square of the hypotenuse, equals to BC squared plus CD squared. Again, BD is the missing hypotenuse, so we leave it as it is. This equals to BC squared. BC is also the missing side, so we leave it as it is, so it is BC squared plus CD squared. CD in total it is 1 plus 4, that is 5. Therefore, CD squared is 5 squared, that is 25. So in total, according to equation 2, we shall find out that BD squared equals to BC squared plus 25. This is according to equation 2, while according to equation 1, we already found out that BD squared equals to AB squared plus x squared. So we have two different equations for BD squared. Equation 1 and equation 2. Therefore, we created equation 3 that states that BD squared according to equation 1 must be equal to BD squared according to equation 2. BD squared according to equation 1 equals to AB squared plus x squared, and It is equals to BD square according to equation 2. BD square according to equation 2 equals to BC square plus 25. So in total according to equation 3, we should find out that AB square plus X square equals to BC square plus 25. In the next step, we implemented the Pythagoras theorem on this, the green tile PBC. According to the Pythagoras theorem, in this green tile PBC, PB square, that is the square of the hypotenuse, equals to BC square plus CP square. Again, in the green tile PBC, according to the Pythagoras theorem, BP square, that is the square of the hypotenuse, equals to BC square plus CP square. But it is given as a equation that BP equals to AB. BP equals to AB. So we can substitute BP by AB. So we can substitute BP in this equation by AB. BP equals to AB, therefore BP square is AB square equals to BC square plus CP square. So in total, according to equation 4, we have found out that AB square equals to BC square plus CP square. But CP equals to 4, therefore CP square is 4 squared, it is 16. So in total, according to equation 4, we actually found out that AB square equals to DC square plus 16. This is according to equation 4, while according to equation 3, we already found out that AB square plus X square equals to BC square plus 25. And because of the fact that AB square equals to BC square plus 16, we can substitute AB square in this equation 3 by BC square plus 16. We did it, and we found out that AB square is BC square plus 16 plus X square equals to BC square plus 25. So in total, according to equation 3, we found out that BC square plus 16 plus X square equals to BC square plus 25. We have BC square on both sides of this equation, equation 3, so BC square will get cancelled. After we cancel BC square on this side of the equation, we left with 16 plus X square, while on the other side of the equation, we left only with 25. So in total, according to equation 3, we found out that 16 plus X square equals to 25. Here we subtracted 16 from this equation, and we found out that X square equals to 25 plus 16 is 9. So X square equals to 9. Here we took out of the equation, and we found out that X equals to the square root of 9, that is 3. We found out that the length of this line segment AD, this equals to X, is equal to 3 units. So we finish with the first method. In the next step, I repeat on the solution according to the second method. Repeat on the solution. That is why we find out the length of line segment AD is equals to X according to the second method. Okay, I repeat on the solution according to the second method. In the second method, we did the construction, that is to say, we extended this side DC of quadrilateral ABC by 4 units. Again, we extended this side DC of quadrilateral ABCD by 4 units. And we defined the edge of the extended line segment, this point, as Q. Again, CQ equals to 4 according to our construction. DC is one side of quadrilateral ABCD, therefore it is absolutely a straight line. And when you extend a straight line by straight line, the result DQ is also a straight line. So DQ is a straight line. If you focus on the upper side of this straight line DQ at point C, here the sum of the angles must be equal to 180 degrees according to all three. All three said that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line DQ at point C? We have this angle that is the right angle plus this missing angle, so the sum of those angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in size. In the next step, we join points B and Q together by straight line. When joining points B and Q, we get the right triangle BCQ. So in the next step, we prove that those two right triangles can go into each other according to sine against sine rule. So why those two right triangles can go into each other? First of all, PC equals to CQ equals to 4. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, BC is the common side that belongs to both targets, so we can write down that BC equals to itself as a common side that belongs to both targets. So we found out that those two right angles can go into each other according to sine against side rule. And again, we found out that the right angle PBC congruent, this is the sign of congruent, to the right angle BCQ according to sine against side rule. What is sine against side rule? If we found out that those two sides and the angle that is included between those two sides, this angle, this right angle PBC are consequently equal to those two sides and the angle that is included between those two sides, this angle, this right angle BCQ. And therefore, those two right angles can go into each other according to sine against side rule. We have those two sides and the angle that is included between those two sides in this triangle PPC was equal to those two angles, and the side that and the angle that is included are equal corresponding equal to those two sides and the angle that is included between those two sides in this right triangle BCQ. Therefore, those two right angles can go into each other according to sine against side rule. So, and from the fact that those two right angles can go into each other, we will have that their corresponding sides must be also equal to each other in their lengths. According to the rule that says that corresponding sides and congruent triangles are equal to each other, those two triangles can go into each other, and therefore their corresponding sides must be also equal to each other in their lengths. The hypotenuse BP in this triangle BPC is the corresponding sides to the hypotenuse BQ and the right triangle BCQ. So, those two corresponding sides must be also equal to each other in their lengths. That is to say, BP equals to BQ. BP equals to BQ. BP equals to BQ, but according to what is given as a question, AB equals to BP, or BP equals to AB. So we can write down that BP equals to AB, and from this equation, AB equals to BP equals to BQ, we derive that those three lines at AB, BP, and BQ, they are all equal to each other in their lengths. In the next step, we did the construction, that is to say, we draw a circle around point B in such a way that point B will be the center of the circle and BA will be the radius of the circle. But again, we did the construction, that is to say, we draw a circle around point B in such a way that point B will be the center of the circle and BA will be the radius of the circle. So this is the circle that we draw. BA is the radius of this circle, therefore we define the radius of this circle as R, so BA equals to R. But because of the fact that BA equals to BP equals to BQ, and BA is the radius of this circle, BP and BQ must be also the radius of this circle, that is equals to R. So we know that those are the three radii of this circle, BA, BP, and BQ. But what is the definition of a radius? The radius of any circle starts from the center of the circle and ends on the circle itself. So BA starts from point B, that is the center of the circle, and ends at point A, that is the point of the circle itself. That is to say, this circle must pass from point A. Likewise, BP is also the radius of the circle, and therefore this circle must also pass from point P. Likewise, BQ is also the radius of the circle, therefore this circle must also pass from point Q. So in total, we found out that this circle must pass from points A, P, and Q. We know that according to what is given us in the question, this is a right angle. That is to say, if this is a right angle, it means that DA is perpendicular to AB. According to what is given as a question, DA is perpendicular, this is the sign of perpendicular, DA is perpendicular to AB. But according to our definition, BA is the radius of the circle. So I can write here that BA equals to R, it is the radius of the circle. So from this equation, we derive that DA is perpendicular to the radius BA. DA is perpendicular to the radius BA, and therefore dA is the tangent to this circle at point A. dA is the tangent to the circle at point A. This is the common point D. From the common point D, we have tangent dA that is tangent to this circle at point A. Likewise, from the same common point D, we have secant dq. Secant dq cuts this circle at those 2 points, P and Q. dP is the external part of the secant, and dq is the length of the secant in total. The product of the external part times the length of the secant in total is dP times dq. And this product equals to the length of the tangent squared. That is to say, dP times dq equals to dA squared, according to tangent secant theorem. Repeat quickly on tangent secant theorem. According to tangent secant theorem, if a tangent and the secant are drawn to a circle from the same external point P, here we have, this is the common external point P. From this common external point P, we have tangent PA that is tangent to this circle at point A. Likewise, from the same common external point P, we have secant PC that cuts the circle at those 2 points P and C. Actually, PB is the external part of this secant, and this secant in total equals to PC. The product of the external part times the length of the secant in total is PB times PC, and PB times PC equals to the length of the tangent squared, that is to say dA squared, or dA squared equals to PB times PC. The square of the tangent length, that is PA squared, equals to the product of the secant's whole length and its external part. The length of this secant in total is PC times the external part, that is PB. So this PC times PB equals to dA squared. So we can implement the tangent secant theorem in our drawing, as I mentioned before. From this common point D, we have tangent dA, and from the same common point D, we have secant dq that cuts the secant at those 2 points. Again, dP is the external part of the secant, and the length of the secant in total is dq. The product of the external part times the length of the secant in total is dP times dq, and this equals to the length of the tangent squared. The length of the tangent squared is dA squared. In total, dA squared equals to dP times dq. So according to tangent secant theorem, if you focus on the common point D, the following equation is to dA squared, that is the length of the tangent squared, equals to the product of the external part of the secant, that is dP, times the length of the secant in total, that is dq. So dA squared equals to dP times dq. dA equals to x, and therefore dA squared equals to x squared. dP is 1, and dq in total is 1 plus 4, that is 9. So in total, we found out that x squared equals to 1 times 9, that is 9. X squared equals to 9. Here we took out of this equation, and finally found out that x equals to the square root of 9, that is 3. So the length of this 97 AD is equals to x is equals to 3 units. So in both methods, we found out actually that the length of 978 is equals to x is equals to 3 units. Okay, thank you very much.